Hello, everybody. Welcome to part 3 of our live event of the webinar series, Introducing AI for Image Analysis, How to Be Successful. Before we start today, let's quickly look into the Zoom room and give everyone the chance to join us. So if you look at the bottom of your screen, you will see the Q&A box, and this is all you need to know today. If you want to post a question or a comment, then please use the Q&A box. During the presentation at any time, we will collect your questions and answer them at the end of the session. So for those of you who have not joined us in the previous sessions this week, my name is Anne-France Carter. I work at PreciPoint as a marketing specialist, and I have the honor to introduce the speakers for today. So I will start with welcoming again today Philipp Kainz from KMLVision. KMLVision is a partner of PreciPoint in the area of image processing. Philipp is the founder and CEO of KMLVision, and he is here today to give you a presentation. Welcome, Philipp. And again, today I have my colleague Birgit Müller, who I don't think I need to introduce again, but I'm sure you know her very well by now. Birgit is Head of Business Development at PreciPoint. And welcome, Birgit, as well. So I will not steal any of your time, Philipp, today, so that we hopefully have enough time to answer all the questions by the end of the session. And today, the topic, we will take a closer look at AI development and what it is that you need to know when you train your own model. So I'm very sure it's going to be very practical again. So let's dive into it right now. And with this, I hand over to you, Philipp.
Thank you very much. So you should now be able to see my presentation. Thanks. Okay. Oh, perfect. So welcome, everyone, also from my side. For those who didn't know me yet, I give a short introduction to myself. I'm Philipp Kainz. I'm the CEO and co-founder of KMLVision. My background is in computer science and biomedical image analysis, and I did my PhD at the Medical University of Graz, where I worked on establishing and creating new methods for automated image analysis in the histology domain. And after some time, I decided that I want to leave the academic world and found the company with a clear mission. So KMLVision sets out to providing intelligent and accessible solutions for the efficient automation of large-scale and labor-intensive image analysis tasks, such as, for example, in digital pathology. And for that reason, we created the ICOSA platform. ICOSA is a collaborative software platform for large-scale image analysis. And it comes with a data management and a data repository, a viewer, and of course, the part that is most interesting to the audience today is automated analysis and AI-backed applications. It's mostly used in regenerative medicine, biomarker analysis, or other cardiovascular research, and many more domains. So let me start out by quickly summarizing the key takeaways from last time, where I talked about choosing a solution that best fits your requirements and prerequisites. So first, pick one use case and define a very clear objective of what you want to analyze. Understand the factual requirements compiled by the domain experts, and of course the technical requirements that are deducted from them. So if you start out with an idea that should involve AI, discuss also with your peers the use case and get their feedback on how to automate this analysis. And yeah, given these requirements, the best solution should be selected according to them. So try to figure out how you want to have the analysis results presented. For instance, if you need a simple counting, you may use an object detection approach. But if you want to have morphometry, use segmentation. And the better you define your use case, the more likely you are to succeed by applying AI to it. And of course, not all use cases benefit from automation using AI, but generally, we also advise our clients that if you have only 4 or 5 whole slide images, the cost benefit is probably not so balanced. And finally, using platform technologies can already take a lot of weight off your shoulders, so you can really work in a result-oriented way. And last time I also introduced some basic terminology to give you an orientation how AI can be implemented for image recognition. So we took a look at image classification, which solved the question, which classes are present, object detections, how many objects are there, semantic segmentation, what is, for example, the area of a particular class occupying a slide, or instance segmentation. So if you really want to go into into depth and analyze particular objects. And today I want to show to you how you can develop your own AI on our Ecosa platform without any coding skills. We have put significant effort also into the product development to present you with the opportunity to use AI as a service right away from a web browser. And it already implements a lot of best practices you find in the life cycle of deep learning algorithms. And to make this more accessible, we provide Ecosa in the cloud, so you're welcome to just sign up for free and try it out. You will also find the sign-up link on our website. So the general AI workflow consists of training, evaluation, and finally using the algorithm in production. It starts as soon as you have set a set of digital images, and we already covered that in the previous webinars, which you can upload then to our platform. And then as next step, you annotate a certain set of these images for training and validation, and you launch the training. So this is basically the third step and completes the training. And after each training, you can take a look at the AI training report, which contains qualitative and quantitative results on a held out image data set to assess whether the model performs already in a way that you can use in production. And then you can decide, of course, if you are already satisfied with these results, or if you want to retrain it, add more data, improve the diversity of the data. So I will now switch my window to show you briefly how Ecosa can be used to perform image segmentation. Can you see the application? Thank you. So basically, our platform, in our platform, I prepared a project, and our task is to use AI for nucleus segmentation. So in Ecosa, we use a project-based approach to organize the image data, which also serves as a kind of workspace that you can share with your collaborators. And I already prepared this project, and we have a couple of images already uploaded. So for the sake of time, I just enter the image library. And within the image library, you see the data set that composes basically the ground for your AI training. So since we are interested in segmentation, we have several image parts annotated with labels. So here we have a label called nuclei, so the semantics and the ontology you can define yourself, of course. But for this showcase, I just created one label. And we did that in many different images. So you can flip through them and see which instances actually have been annotated. And here, for example, I can show you how this works when you identify that there is something not annotated like this here. You select here drawing tool and then the label and just annotate this very coarsely in the image. So there's no need to save anything. Everything is saved and stored in the background. And once you're done, you should make sure that you have a dense annotation as far as this is possible. Of course, for whole slide images, this is not as easy, but I will get to that in a second. So what we have right now is a data set of a certain number of images. And what we now want to do is train a new algorithm to actually segment these objects. And what I need to do is just to open the Ecosa AI. And this takes you to a wizard. It basically guides you through the entire process. And it also shows you some information that you probably need to consider upfront. Many of these I covered in my past 2 talks. So make sure to get back to these recordings and learn about it. So the first step will be to select the project, and we already come from this project that's already selected. Choose the segmentation goal and select which labels you want to annotate to learn. So you can also create multiple annotations in your project and create selective classifiers or selective models only for a specific subset of these labels. And then you select your images, and these images are part of your training and validation set. So basically, you can also check here which parts of the image are annotated and make a further quality control, make sure that they are more or less densely annotated, and then you can review your training. All you need to do now is just enter a name and click on Start Training. And what's happening now in the background is that your training gets queued. So all the data is being collected from the platform. And then when everything is in place, training starts, and you will see a progress bar here. And for the sake of time, I also took the liberty to train exactly the same model an hour ago to have the report ready. So I was talking about evaluating the model. And to show you how this works, we open the report. And what you see here is basically the quantitative results and the qualitative results. The trainings are now, for the sake of demonstration, divided into a training and a validation set based on a random split. So here in this case, the 2 images, train 07 and train 06, have been selected to be evaluated. And what you see here are some metrics that are automatically computed after a training time of about 20 minutes. So the longer you train, usually the better you can get. And here we have also some qualitative results. 1 second, so I need to, here. Okay, so where we also show, okay, how well does the model perform? So it gives you more or less an idea of where the false positive and false negative detections are. And this is quite useful to identify maybe parts where you want to improve the annotation and add more data to your training. And that you get, of course, for each label separately, so there is no cluttered interface. And also here in this bottom right image, you can see everything that's in red is a false positive, and everything that's in blue is a false negative. So the model missed it actually. The green ones are the true positives. There's also some qualitative and quantitative result metrics in the appendix of this report, and it should be self-contained to allow you to assess whether this is already of sufficient performance for you. So here we see that the training is already progressing, and yeah, that's basically covering the entire training process and the evaluation process. And now if you want to use this model, you deploy it. So it's basically available to all your projects within the platform, and you can immediately start out and analyze new images with the newly deployed and newly trained application. And just by switching into the project, you will see that the nucleus segmentation is already here. And submitting jobs for new images is as simple as clicking on it, selecting the image you want to analyze, and start the job. And after some time, it's usually not that long, you will get here the results. And the results are also presented in a quantitative and qualitative way. We have regions of interest, so there's plenty of opportunity to also push through whole slide images without actually analyzing the entire slide. And yeah, that's basically what you can also expect from the numeric results is a lot of morphometry data, like the area and circumference and stuff like this, that's automatically extracted. Okay, and now I'm switching back to my presentation. Okay. Do you see it? Birgit or Anfras? Okay, thank you. So concentrated. So let me just summarize what I just showed you in this brief demo, and which challenges may occur when you develop your own AI. So data generation and slide digitization we already covered in the last webinars. So data selection actually is quite important, and especially to make sure that you have really no overlap between these data in training, in validation and testing, because you want to make explicitly sure that you create a model that generalizes and does not just learn training data by heart. And using the annotations and marked the respective image regions. And we defined some semantics for this image data. Data quality assurance can be quite challenging, but in general, it makes sense to compare different labeled regions across different images and rule out outliers that may confuse the model. We have also tools for that in our platform. And pay close attention to the performance of your trained application. Make sure that you create a representative data set that you only use for benchmarking, so that when you train more and more models, you have a reference. Here you have some challenges that are frequently described as the domain shift. There may be the case that when you have only one scanner and you train your model on that it won't perform as well as on another scanner, because the sensors are different, the lighting conditions are different, and so on. So there are different techniques to approach this, for instance, data augmentation, or also fine-tuning the model on new data, which I also covered in my previous talk. And some best practices would be with the goal in mind that we want to present unambiguous data to the model, is provide as much information as possible, because the more information you present, the better you can train the AI. If there are too many similar objects within the data set, this may not represent the real world and leads to poor performance. Annotate more images in smaller regions of interest is usually better than annotating an entire slide. Especially when working with colleagues, make sure that data hygiene is also taken care of. And if you're in a big lab, try to avoid this domain shift by including images from multiple scanning devices. I've if you present the model with the image as it is shown here, it looks basically at all the regions. And you can see that some of these objects are annotated, some are not. And achieving a dense annotation, which usually is the best case to provide data to an AI for segmentation, is virtually impossible on a whole slide. So what people usually do is create these sparse annotations, and this means that not all objects are fully annotated. So if we would use this one as training image, as training image, the model will have a hard time figuring out why in the green square the object should be detected and in the red square it should not be detected. And a good practice here is that you restrict this region by using a region of interest and focusing the model's attention. Another aspect to consider is the prediction runtime of such a trained algorithm. And for instance, if you would analyze a full slide, it makes take some time depending on the magnification, even consume a lot of computing resources. And to reduce the time the model needs to see all parts of this image, we apply sample detection at a low resolution. And this significantly reduces the runtime, and the analysis can be performed, let's say, on a fraction of the original slide. So key takeaways. The first one is different use cases may require different approaches. So this is quite clear when you take a look at how you can formulate an AI problem for image analysis. Then establishing AI solutions is an iterative process. This sounds like a broken record, but you have also seen that you may go back and forth when you're not satisfied with the performance. It's an empirical work you need to put in there, but in the end, it will pay off. And being involved in building these solutions creates trust also in this new technology. So as much as possible, try to be involved in these projects. And there are no code solutions, as I have shown you right now, that may help you solve your use case. And try to get your hands on a product and evaluate it according to your requirements. So feel free to reach out. We can already set up a demo or some hands-on experience for yourselves. You will find LinkedIn contact information in the webinar. Also visit our websites. And in addition to that, we also offer a guided trial period of up to 4 weeks, during which you can get workshops and consultations on image annotation. We answer the most pressing questions regarding the product, the data, AI training, and so on, in the context of your specific analytical challenge. So, and speaking of hands-on experience, the final part of our series, David Hercher, will, from the Ludwig Boltzmann Institute of Experimental and Clinical Traumatology in Vienna, is going to talk about a very exciting use case from neuroregeneration tomorrow. And I'm really looking forward to hear his opinion on and experience using eCOSA for the analysis of histology slides. And by that, I conclude. Thanks for your attention. I'm looking forward to the FAQ.
Thank you, Philipp. Thank you very much. I will take over again the screen in just a second. And with this, I will open the Q&A session. And I invite my colleague Birgit to start with the first question we've had in the Q&A today. And if you have more questions, please, you can enter them now.
Yes, thank you, Alphonse and Philipp. Very interesting to also see how it actually looks like. Maybe, Philipp, we can already go back a little bit. There is a question, or actually a two-part question around, I think, what it is that you have shown. And the question was, what is the goal of the analysis that you've shown? Is that to count the number of nuclei?
It's a side product, actually. So This use case was performed by one of our collaborators, and they were interested in analyzing mouse prostates. And they were not really sure if so these were disease models, but they weren't really sure if the needle biopsy really hit the tumor. And we're also interested in characterizing normal adjacent tissue and correlating that with profiling from molecular biology was of their interest. So this is not related to the cell counting itself. It's really understanding the distribution, for example, of nucleus sizes and trying to match that to a different goal.
Would nuclei counting also work in a similar way?
Yes, you can formulate nuclei counting as well as a segmentation problem. Would work like this, and there's also another approach like object detection. But usually for object detection, you need much more data because the input space the network or the AI sees is not actually the entire image, but just parts. And you have, with the pixel, you have much more data you can feed to the network and train deeper structures.
Now that we are on the topic of how much data do you need, is there some kind of a rule of thumb for how much data you would need for certain applications?
I think it depends strongly on what you're trying to solve. It's always, I mean, I get this question like every time. It's not so easy to say it's 5 images because it depends on how large your images are, how diverse they are. Usually, if you are sure that it represents what you're trying to solve, or everything that you're trying to solve is represented in these images, also 10 images could be sufficient. And I'm not talking about whole slides, I'm talking about regions. And we have also seen this work, not in a context of histopathology, but for transmission electron microscopy, where it's working on 10 images really well, even after 20 minutes of training. So that's more or less the iteration you can expect.
Interesting. Then is there a secure source of data sets website that you can use? Do you know of these?
I mean, yeah, there are some. Of course, if you check the academic literature, it has become best practice actually to also publish your data with your paper, and this really makes sense, and it has many benefits. However, you also need to be sure that the data was quality controlled. So even if you're taking some public data set, have some expert look at this and just don't take it as it is. Of course, if there are millions of images, the label noise may also be just ruled out by enough data. But in general, websites such as the Genome Atlas, you can use, for example, where you find labeled images also from histology, and train on that. Other sources would be Kaggle, for example, a common platform for machine learning problems where also companies post their challenges, and you can participate in these challenges. And of course, this data is not for use in any commercial setting, but for a research purpose, mostly you can get some approval.
Interesting. Maybe, Philipp, if you can type the names of the web pages into the chat, I think then everybody can see. They don't need to Google for it.
Okay.
Meanwhile, another question I have is, how can I know how well my model performs?
So one way to do it is to look at this qualitative and quantitative data. So usually what you want to do is first take a look at, do the numbers work for me? And if, for example, the numbers are off the charts and don't really have anything meaningful to express, then you probably should add more data. Sometimes it's not sufficient to just look at a single number to determine if the model is working correctly. So you need to have additional visualizations and qualitative results. For example, take the case where you have an extremely unbalanced data set. So let's say cell type A and cell type B, they are in a ratio 20:1. So if the model now learns to recognize where more data is available, it basically makes no error if it always predicts the same class, right? So you will get very high quantitative results and metrics, but in reality, it fails on a lot of, or maybe all of the underrepresented classes.
Yeah, very good point. I think that's also usually why we would suggest to take, samples from real life, not try to necessarily come up with different ones, because then you might overfit the sample set in a way, right? So it's good to take just what you have, because that's usually what's most representative.
Yeah.
And France, how are we on time? Do we have time for one more question?
Okay, we're a little over the time, but I think there's one last question. So I would suggest we answer this, and then we'll wrap up.
Perfect. I hope, Philipp, it's an easy one. So when you want to do nuclei segmentation, what framework is the one that you would use for the best accuracy, highest accuracy?
Framework in terms of technical framework, or I'm not sure I'm getting the question correctly.
Maybe the one who typed the question, OpenCV.
Okay. You mean like the tools? So OpenCV is definitely one of the components that we also use in our stack, and it's more or less standard in the industry. There are different frameworks. You cannot really say use a specific framework and then you get maximum accuracy. There are, for example, implementations in TensorFlow and PyTorch and whatnot of the same model architecture. So it really depends on how the solvers and everything around the model is implemented that determines whether you get earlier or later to your maximum accuracy. So it's not about the choice of framework or tool. It's more about whether you phrase your question correctly and support this with sufficient high quality data.
Thank you. I think that was relatively straightforward, and it sounded easy from your side, at least.
Very good, very good. So this is it. We've reached now the end of the Q&A, and thank you for everyone for being so interactive today. So again, we will see you tomorrow for the final part. This will be very exciting because it will be a great way to look at an example, a real life example of using the ICOSA platform for neuroregeneration. So we will see you tomorrow at the same time. And in the meantime, of course, feel free to visit us or contact our speakers if you have any additional questions or need some information. And that's it from my side for today. Thank you all very much again. Thank you to our listeners. I hope you enjoyed it, and I wish you a very nice rest of the day.
Thank you. Bye-bye.
Thank you, everybody. Have a nice afternoon, day, wherever you are.